Then I'll just take it away. And let me first introduce you to the agenda for today, for my little talk here. I'm going to talk a bit on a few introduction things like some definitions, etc., and what this talk is about and what it's not. And I'm heading over to reproducibility and the associated crisis, going to talk about countermeasures and the missing links from reality and what we could do as RSEs. So, as this is the RSE track of the software engineering conference, I'm not going to bother you about what is software, what is software engineering, etc., 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 which I'm usually, when I'm targeting a broader audience, I'm talking about that too. If you have any questions left, there will be slides available. I've linked them in the pad, and you're invited to just click those links and read up everything that I, for now, presume that you know it already. So, what I'm going to talk about today is to remind all of us about the data software environment codependencies, which is often neglected. Then I'm gonna get to the point of what is reproducibility and what is the associated crisis, where does it come from, what is it about? And then head over to what's actually something like provenance. You might have heard this already. And why do all of these things matter to us RSEs? And how does it relate to RDM? Why should we even take care of this? So, as promised earlier, I'm going to keep it short on the theory part. I just wanted to add my short definition of what is research software. And for me, this is any code written with the intention to attain novel scientific knowledge. And I'm going to use this implicit during my talk. So please, if I'm calling something software, I'm usually referring to research software, or not software you're buying, etc. So let's switch to right in and talk about this software thing we are usually approaching in our daily work. And in many cases, or I'd be tempted to say in all cases in modern research today, there is some kind of code you writing as an RSE, and then there is data, and you're usually going ahead and use the data within your code, or you're generating data, or whatever. So there's a direct link between data and code, and it's a codependency because one doesn't live without the other. But not to forget, code always runs in an environment. Like you're running some kind of operating system on some kind of Python or whatever language you're using. Still, it's an environment. And you should be aware that those environments might not be the same everywhere. So there's always a triplet. And it's always true that also data has a kind of environment. Maybe this is mostly about the physical part. For example, when you're measuring data, this is dependent on the measuring equipment, etc. But sometimes there might be also other cases where, for example, the environment dictates the data format or whatever. So you're always going to have a triplet of data, software, and environment. And you'll be, it would be good advice to not neglect environments in practice. And sometimes this seems like it has been forgotten. But you'll need to be aware of this triplet because all of this will influence your results. The scientific results you're then trying to sell to the world as a new scientific knowledge, which was great, but well, you're still depending on all this stuff. So when we're having research results, in today's research, there's a common practice of asking someone who's publishing results, hey, is this reproducible? Can I, assuming that I have the same data and have the same analysis, can I get to the same conclusions or to this even to a reproducible result? This is quoted from the Turing Way guide, and I adapted it slightly because there are some differing definitions of what is reproducible, but I'm going to use this one here, this definition here. And for me, analysis is then the case of having software and environment, and to make the triplet complete, you'll have the data in the columns. So it's not a big deal. Software and data are a foundation of most results, right? There seems to be some kind of crisis. This has been discovered at the early 2010s, and there has been a Nature study on this even in 2016, which has been the most or the most prominent and the biggest study on this, which has been made in form of a survey of over 1,500 scientists. And well, as you can see from that graph, which is quoted from that publication, that there seems to be a crisis. At least many scientists are convinced there is. And it started actually in social and medical sciences. And countermeasures for this are still ongoing. Well, if you're not into social or medical sciences, well, you might think you're safe, but let's take a closer look. Things become brittle when, first of all, there's a lack of strong basic theories in nutrition on controlled experiments. Well, what's that about? Peng says in his publication that, for example, in medical sciences, you don't have that much of controlled experiments or theories like you'll have in astrophysics. That's quite natural. So let's get to the next one. In many research cases today, you'll find some kind of AI or machine learning application. But often people are blindly relying on some kind of black boxes. So the field of explainable AI is a huge new research field, which is still growing and is still not fully addressed. So you need to be aware that when you're using some kind of machine learning algorithm, there might be problems with reproducibility because, well, there's an example later for that. Then what if in your case, publish or perish hits you? There are cases that the pressure for publishing in high volumes in high-ranked journals, and also the habit of not publishing bad results, like, oh, this doesn't work, then let's better not talk about it. And not to forget, I'm Hannah. Of course, things also become brittle when peer review fails to detect stuff. Like, you might remember that in the natural sciences, there had been that very large scandal about cold fusion, which is, I think, in the 1970s. So we're all not safe from this stuff. Of course, even for today, data software and environments aren't specified or available. So then you'll run into trouble when you're trying to reproduce things and nobody talks about what you're actually using and where does the data origin from and where can I find the software, etc. Let's take an example. Just for a moment, imagine you'll train an AI model with some training data. Fine. How do you ensure this model can be trusted? Well, what happens when you train it again? What happens if the model is applied to new data? What if you didn't notice your selection bias for your training data set? What if you share your model, but, well, you couldn't have somebody else reproduce it because, well, you didn't share data in code. So this is kind of that black box problem I mentioned earlier. What if you actually did share it, but you didn't communicate this very well? Well, then something happens, which, for example, happened to some research scientists at Harvard. They published a breast cancer AI model to diagnose new kind of stuff with the help of an AI model. And then a reply to that publication came out, made by Hyber Keynes. And they said, well, this is all very nice. It's all such a nice AI model. It's so nice to see that such methods are a good thing and that they are fostering the new methods, etc., etc. But we haven't been able to reproduce all this stuff because we couldn't find the data, we couldn't find the software. So is this actually of great use? Well, they shouldn't have been so fast or taken a closer look. And there has been a reply to the reply, which is McKinney 2020, where they say, well, we did publish all this stuff. You can find it here, 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 and here. but they didn't do all these things in the first publication. So this is kind of a trust, communication, and citation issue. What if they would have referenced all their stuff, like the data and the software, etc., in proper publications, or when they had data publications and software publications, that they could have cited it, and it would be more easy to find them. So let's take a look at countermeasures for all these hazards that are upon us. Let's first of all concentrate on a section of reality and not the entire research life, which is, for example, things like you'll receive data from an experiment, run different analysis on it, and then merge it together to create some kind of text publication or results publication. Or you might run the same analysis for different things, different data from different experiments, etc., and compare that. So this is already some kind of workflow, but it's not really complicated. It's just from left to right, and that's it. In this case, many people use research IDEs. For example, here, let's start with the proprietary flavors like Origin, MATLAB, IDL, Stata, and so many others. This has advantages, like especially over spreadsheet applications, like you'll have decoupled code and data. Great. They are interactive because you can play around with your data and your software, etc. And usually you'll only require minor skills of programming. So this might sometimes not be in something that in RSE is really is hard to address for an RSE. Some support version control systems and test frameworks, and sharing is certainly possible, but there are also drawbacks, like licenses of all of these tools are quite costly. And especially when it comes to extensions, you might be tempted to use them, but how do you make sure that some other scientist that doesn't have a license for example, for a MATLAB extension, is able to reproduce your results then? They can have the data, they can have the code, but they might not be able to run it. There is a solution to that, at least. You could use free and open source systems of research IDEs. For example, you could use Jupyter Notebooks, or RStudio, or Octave, or something else. And all of this is greatly is integratable within version control systems, testing, etc. It's easy to archive because it's free open source, so you can include it in your archive. And it's easy to share because everybody else can just download it from the internet and they don't have to pay a license fee, etc. Well, we are actually here approaching the traditional software engineering methods we are used to as RSEs, but it's still great that it's so interactive and you can play around and test things very easily, which is very tempting in science and research. But be aware, there's a discussion about if notebooks are junk food. There are problems, but you can address them. A good advice here, which has been brought to my attention, is take a look at Notebook Dev by FastAI. You can also run research IDEs as a service, which is very convenient because it's usually browser-based. And for the OSS flavors like Jupyter Hub, etc., which you can install on premises, there is also the possibility to use local HPC resources and just be near to your big data sets you might be analyzing. There are also options like paid options like CodeOcean, Wholetail, MyBinder, etc. Some of these can also be used locally, but well, I'll just place a word of warning here. When you're using these paid ones, be aware there might be vendor lock-ins, and it's not fully clear whether there are legal issues when, for example, you're using some kind of service like CodeOcean in the US. So all of this is very nice, but reality tends to be more complicated. Usually, as an RSE, you're more familiar with this one here. There's software involved in the analysis. There might be different software versions involved in the analysis. And you'll be suddenly asking yourself, hey, what happens if I'm running the same code for different data? Is it still the same result? What happens when I'm using different parameters? What if I chain multiple code and data steps? What if I transform a step result into three new steps, or all this complexity growing into some kind of graph, like depicted here? What if I'm adding even more, not depicted here, like involving different environments? And now your colleague is trying to reproduce all this. Can you trust your results? And even more important, can you trust such beasts that someone else is sending you? How could you be possibly make sure that you really know what's going on? There's stuff that helps with this. Let's transform these parts of reality into two different things. First of all, pipeline workflows. These flows you've seen earlier, those arrows targeting from one place to the other. This is actually data being moved around by some either manual or computational process. You could use the pipeline for this and describe that, so you can automate it, or at least have it run by a computer and not moving it around manually. There are distinguished tools for this in the form of domain-specific languages, for example. And the most prominent for this would be the Common Workflow Language, Nextflow, and SnakeMake. There are others. I've listed a few there. There might be more. And on the other end, as I've said earlier, these are graphs. So as we know from computer science, these are directed graphs because we have a direction here. And those nodes and edges can be represented. And there are also tools for this. They might not be widely known with us RSEs, but there is a huge community already around it and within the RDM space. Like, there are knowledge graphs that allow you to describe these graphs very, very distinct. There is the topic of data lineage, which is already addressing all these obstacles about, hey, where does my data come from? Where does it go? And of course, there's provenance. It is kind of the broader topic of data lineage. Pipelines have pros and cons. First of all, of course, on the pro side is you will have loose coupling of data and code. And you're going to reuse existing codes here, or at least you'll have the possibility. You can use your old Fortran library within a step of your workflow, which might be hard to address within a notebook, for example, or a Jupyter notebook on Jupyter Hub. It's, of course, possible to reuse stuff like notebooks or R within steps of your workflows, and pipelines are ready for this. That's fine. And it's easy to reproduce as you're describing it in great detail. Everybody else could reproduce it by using the same command and using the workflow engine. It's easy to share and reuse. A workflow can be described in certain formats, and they can be shared, for example, on workflowhub.eu, which is a growing platform for sharing all this. It's self-documenting because, well, you're actually describing what you're doing, and it plays well with tools like Singularity, GUIX, and all things HPC. So you can also respect environments here. But to all those goodies, there are cons, like obstacles in the form of, hey, this is even more work. You need even more new skills. And all of this has a steep learning curve because the ecosystem is not yet grown up. And also, it's not that integrated into RDM infrastructure. The future holds new stuff for us. There are, of course, things like CVL Prof to automate all the hard work. Like, you want to create a provenance file from your workflow, no problem, here you go. So you don't have to write all these shiny graphs by yourself, but use a machine on the go while you're executing the workflow to take a look at it and have it recorded for you. There's a new format approaching standard RO-Crate, which is trying to bundle stuff in distributable packages when you need to exchange stuff. Like you'll have a research object and you're trying it to combine with the provenance of the research objects, with workflows, resources, where do they come from, etc., data lineage, and trying also to associate with who was involved, under which licenses does all this happen, and so this is kind of a format to describe the whole graph I've showed you earlier into one standard file format. And for the more complex things, like we want to have interoperable electronic lab notebooks or want to capture the data generation process, there are even more sophisticated stuff like knowledge graphs and ontologies using, for example, SciMesh or metadata for Ing, which has been recently released. For the future, I'd like to propose a call to action. What could we do as RSEs? First of all, we could make sure that research projects get well structured. Note here, please, the usage of data-led and manage. Especially data-led is a very great tool to make sure that you're not hosting large files within Git and keep track of data anyway, when that comes from different resources in different places. Next would be to make environments reproducible. Use good practices and go for Singularity, GUIX, Honda, and other similar tools. Use citable, or go ahead and make your software you're writing, make it citable and referenceable to real publications. I'm mentioning here Stefan Druskat's citation file format, and he also gave a talk earlier, I think this was on Wednesday, about Hermes. And disclaimer, I'm part of the Hermes project, about automating software publications. And more for the far future would be pipelines have the same one-click experience as research IDEs have today, like run this workflow now and make it more accessible, or this whole ecosystem more accessible to academia, because it's quite cumbersome right now. Always remember, please, with all of this reproducibility stuff, you're not alone. First of all, there's ReproHacks, which is a great resource about having hackathons of internal peer reviews, where you'll just try to team up and say, hey, here's my publication. Would you please go ahead and try to reproduce my results, and then the other way around. And if you'll need any expert advice, there's a good place to go to, which is the German Reproducibility Network, which is still seeking for members. And of course, as many links in this presentation are to the Turing Way project, this is the place to go to for all things reproducibility. Please take a look at this very, very sophisticated guide, which has lots of good things and goodies hidden in a very large code base, text base. Have fun with that. So that's it from me. Thanks for watching.